In today's video, we are going over acid-base chemistry. We're going to first talk about Bronsted-Lowry acids and bases. Now, a Bronsted-Lowry acid is one that can be a proton donor, so it can give a proton. And a Bronsted-Lowry base is one that can accept protons, so it's a proton acceptor. The pKa is a value we use to measure acidity. The higher the pKa, the weaker the acid. One of the ways I like to think about it is that, so high pKa values means it's a weaker acid, and lower pKa values means it's a stronger acid. This is kind of opposite, right? So if you lower the pKa, you have a stronger acid. So just remember that this is an opposite relationship with our pKa. Let's look at pKa's together. So when I have HA, like I have drawn here, this is our acid. And when it loses its proton, this A- would be labeled as a conjugate base. I have an equilibrium arrow here. Now remember, these equilibrium arrows mean that all of these species can be present, right, at the same time. Now the KEQ is helping us understand. The KEQ is essentially saying, well, which side of this reaction is favored? Okay, all the species can be present in the same solution all together, right? So we've got our solution of water, and then we have HA as an acid, and we're just trying to understand, well, how much of it is A-, this conjugate base, and how much is it HA, okay? Let's practice our arrow pushing mechanism to see if this even makes sense that an A- will form. So HA is our acid, so I'm going to take the lone pair from water, and I always start my arrow at electrons. So I'm going to draw it to my hydrogen. The HA bond needs to break. So I'm going to draw a second arrow showing the electrons between the HA bond are now going to go to our A. So we have an A- with 8 electrons around it. And then our water now has picked up another hydrogen. We've lost our lone pair from water, right? Okay, so this Bronsted-Lowry acid, this HA, has now donated a proton. The KEQ is simply looking at how much of each species do we have present and where does the equilibrium lie. This reaction is in water, which we know is in excess. So we're going to multiply each side by the concentration of water, which means we have a KEQ times the concentration of water. Well, this gives us this Ka, which is the dissociation constant. The dissociation constant just means how likely is it for this HA to dissociate, to become A- and an H+. If you have a very large Ka, that means you have a very strong acid. So, a large Ka means you have a lot of dissociation, a lot of HA going to an A- plus H+. Again, strong acids are really good proton donors. So this makes sense that a large Ka would essentially mean you have a lot of H+ and A- forming. This dissociates. Now, organic chemists don't like to deal with really large numbers. These Kas are huge numbers, okay? Really large. So what we've done instead is we've taken the negative log of the Ka to give us our pKa. And this then is in numbers that are easier for us to manipulate and to compare. Because we take the negative log of our Ka, the pKa relationship between strong acid is now kind of flipped. So before I said large Ka is strong acid. Well, we take the negative log of that Ka. So it still holds true that a small pKa means it's a stronger acid. And a large pKa means it's a weaker acid. Now, in this class, we're not going to be focusing on these concentrations of different species and calculating this out. We already have a list of pKa's we're going to use and compare them. I just wanted to show you a little bit of the math that is behind where we even get pKa and why is this relationship kind of opposite. So again, lower pKa numbers mean stronger acid. Higher pKa numbers mean weaker acids. Here I'm showing a list of pKa's for a variety of molecules. I'm going to give you something that's a little more, what's a good word for it? General, okay? These are very specific pKa's, and pKa's, it depends on how you measure them. Now, this is going to be listed in an appendix that you'll also have access to for your exams. So I wanted to go over it a little bit. What you'll see here is that there's a list of acids, and the hydrogen that it's talking about is highlighted in red. So, for example, here we have HBr. HBr has a pK of -9. This hydrogen on HBr is quite acidic. It has a very low pKa. -9 is very low. Let's go over to something that has a much higher pKa. Let's go down to, let's do methane, okay? This hydrogen here has a very high pKa of 50, all right? So this is a very weak acid because it has a very high pKa. Now you can use this table to get an idea about what does your molecule have, right? As we look at the table, you're going to see lots of functional groups, and you'll be able to use it to identify what kind of protons do I have on my molecule? Is something acidic? Is something going to happen to this molecule if it's in the presence of a base? This is going to help you analyze it. It will be worthwhile to go through it. What I want to do, though, is I want to provide you with something that has a general trend of acidity, something that will allow your intuition to kick in. I like to do it based on values of 5. Let's start at -5. This is a generic scale. Something that's -5 would be very acidic. So like HCl, you could have a protonated carbonyl. H2SO4, very acidic. I'm going to highlight the protons we're talking about in red. What about a pK of 0? This would be if you had an ether that was protonated, or protonated water, which is hydronium, or a protonated alcohol. These would be around a pK of 0. Let's label the hydrogen that's acidic here. All right, let's move to a pKa of 5. pKa of 5 would be represented in a carboxylic acid here. This proton right here has a pK of around 5. A protonated aniline also has a pK of around 5. I should make a note that when I write R, remember that this is a substituent. Generally speaking, R groups are typically sp3 hybridized carbons, or they could sometimes be H's. These are not functional groups. Let's now move up to a pKa of 10. Hydrogen cyanide, the proton here has a pK of 10. A thiol, which is a hydrogen on this sulfur, has a pKa of 10. You can also have a protonated amine. Now notice this amine is different than the aniline. The R groups here are not aromatic. Let's highlight the hydrogens we're talking about. Another important one would be a phenol. A phenol is an alcohol, this OH group, that's attached to an aromatic ring. So this hydrogen here is also about a pK of 10. Let's now move on to a pK of 15. One of my favorite groups that has an alcohol. Here we go. It's this hydrogen here that has about a pK of 15. Water also has a pK of around 15. A pK of 20 would be a proton that is right beside a carbonyl. I'm going to write this R group here. If we move up to a pKa of 25, this carbonyl also has an acidic proton, but it's not quite as acidic because instead of just an R group, we now have it's called an ester. Instead of an ester, you could also have an amide here. And again, this proton that is right beside the carbonyl. So this is considered an alpha proton, but that proton there is around 25. There's also one more important one here. This is the proton here on a primary alkyne. Okay. This proton here on an alkyne, and this proton here is around 25 as well. I've got room for one more up top. So 35, a pK of 35, we're going to jump 10 units. This is a proton that's on a neutral amine. So these are not that acidic. I'm going to label just a few more. These are very weak acids. They do not like to lose protons. A pKa of around 45 would be this hydrogen gas. Also, this proton here on an aldehyde. This is different than the protons we listed earlier. This proton is directly bound to that carbon of the carbonyl. This is really not acidic, okay? Very high pKa. And then you can get to 50 and above. This means they really don't want to lose a proton. And this is when we're talking about sp3 hybridized carbons with hydrogens. Think about like methane. In fact, it's so high, it's actually difficult to accurately measure. This does not want to lose a proton. So now that we have a generic kind of look at this, we're going to learn what this means and how we can use pKa's to determine if something can act as an acid. Let's do an example together and using our pKa's to determine if something can act as an acid or a base. Typically, you're going to get two different compounds, and you have to decide which one can act as an acid. So let's just start with one option where we're going to have this amine act as our base, and we're going to have the alcohol here act as our acid. Let's draw an arrow pushing mechanism using curved arrows. Remember, curved arrows are just electrons. This means two electrons are moving. It's a way we can communicate what's happening. So instead of us writing out words that says the lone pair of the nitrogen picks up the proton of the alcohol and the electrons between the oxygen-hydrogen bond reside on the oxygen. Everything I just said can be depicted in two arrows, right? So this is really cool because organic chemistry can be communicated with just some pictures and arrows. It's really a neat language. I'm going to draw an equilibrium arrow, and we're going to talk about if this is an equilibrium and which side it is favored. So I'm going to highlight the acidic proton in red. Let's draw what we have. After you draw an arrow pushing mechanism, you always want to draw what didn't change. We have a carbon, carbon, and a nitrogen. And that nitrogen had 2 hydrogens coming off of it. Now our arrow pushing mechanism showed the lone pair now has a new bond to the hydrogen. So the lone pair electrons are in this bond. We just picked up a proton, okay? This nitrogen lost electrons, essentially. You can calculate the formal charge and you'll see that it's positive. We also have an alcohol here that lost a proton. Notice that on our first arrow, we removed that proton and our proton is here. On the second arrow, the electrons between the hydrogen-oxygen bond moved to the oxygen. Before we just had 2 lone pairs, and now we have 3. So these are the 2 lone pairs we originally had. Then we have a 3rd lone pair here. One really important thing to recognize is that everything on the left side of our reaction, when we look at the charges, it's neutral. This should be the case for the right side as well. We didn't lose any electrons. They're all within the 2 molecules we have. So the charge should equal neutral, 0 on the right. So when we look at the right side, we do in fact have 0. We have a positive and a negative, which cancel each other out. What we're going to do now is we're going to look at the pKa's of the left and the right side of our reaction. Remember that pKa's describe acids. And the easiest way to remember that is it says pKa. Okay, pKa. That's how I like to remember it. So it only describes acids. It's just describing how likely that proton that's in pink is willing to leave. The pKa of an alcohol is around 15. Now we're going to look at the right side and label our pKa. The pKa of this acid here is around 10. It's a protonated amine. And we can look back at our previous slide and see that that's around 10. So the first step of doing any equilibrium acid-base reactions is to 1, draw the acid-base reaction, which we did. We used curved arrows to do so. We checked our answer by looking at the formal charges, seeing if it made sense. The second one here is to analyze the pKa's. Now, we just highlighted the pKa's, but we need to analyze them now. I'm going to give you a set of rules that will help you determine if this reaction is in equilibrium or if it isn't. And if it is in equilibrium, which side is favored? So if the difference in pKa is less than or equal to 6, then it is reversible. The difference in our pKa here is around 5. So this reaction is definitely reversible. If the difference is around 10, you can still show it as reversible. Although the larger the difference in pKa, that means one side is very favored over the other, okay? But it's still reversible. In cases where the difference of the pKa's are greater than 10, this is irreversible, okay? Right now I have an equilibrium arrow shown. We know that that's correct. It is reversible. But the third step here says the equilibrium favors the weaker acid or the higher pKa. Weaker acid, higher pKa. Don't forget that. So the lower the pKa, that means it's a strong acid. The higher the pKa means it's weak. It's useful to keep reminding yourself of this. So the equilibrium favors the weaker acid. This is going to help us redraw our equilibrium arrow. Before I had it showing that both sides are equal. Our equilibrium arrow, if we draw it where both of the length of the lines are the same, this would mean that it's equivalent. It's like 50-50 on either side. You can draw an equilibrium arrow where it shows that one side is favored or the other, simply by changing the length of our arrows. And then if you draw a reaction arrow that just has one arrow going from reactants to products, this means it's irreversible. Okay, so here's our equilibrium arrow. Let's now look at what we have. So we've got a pKa difference of 5. Our alcohol is a pKa of 15. Our protonated amine has a pKa of 10. We know that the left side of this reaction is in fact favored. So when we draw our equilibrium arrow, we are going to show that it's reversible, but we're going to show that the left side is favored because it has a weaker acid. And that is why we draw our equilibrium arrow showing that the left side of this reaction is favored. All right, now you might have asked yourself, well, what if we draw it the other way? Let's draw it where the amine is acting as the acid. We can do this and then see if this makes sense. So we're going to have this act as our acid, and we're going to have the alcohol act as the base. So I'm going to take my electrons from the oxygen. I'm going to pick up a proton from our acid that we've decided we're going to try. The hydrogen-nitrogen bond breaks, and those electrons go to our nitrogen. We need to draw this arrow, but we're not sure which way this reaction is going to occur or if it can occur. So let's just draw what we have here on the right side. I have a carbon-carbon nitrogen. Okay, I still have one proton here. The nitrogen started with a lone pair. And now, because of this arrow 1, it has an extra lone pair. This arrow 2 is showing electrons moving to the nitrogen. And that lone pair is shown here with a formal charge on our nitrogen. We also have our alcohol here. Nothing changed with the alcohol, except now it lost a lone pair and it picked up this proton that we are wondering if this can act as an acid. Okay, so let's draw in our proton that we added. We still have a lone pair, and this oxygen is now positively charged. Now let's do our next step. So we drew the acid-base reaction with curved arrows. Now we need to analyze the pKa's. Okay, pKa. We know that pKa's describe acids. So the proton here of our amine has a pKa of around 35, if you look at our previous slide. And if we look on the right side, we see that we have our acid here, and the pKa of our protonated alcohol is around 0. Well, the difference between these two pKa's is 35. A difference of 35 pKa units. That's huge. So as I'm looking at this, the difference is greater than 10. That means it's irreversible. And we know the equilibrium favors the weaker acid or the higher pKa. So in this case, our reaction doesn't even occur. In fact, it's not even going to happen. We can draw it on a piece of paper and show these two molecules reacting. We can draw the arrows, but when we analyze the pKa's, we see that it can't even occur. The left side here is favored, and it does not go to the right side where we have our products drawn. So this reaction doesn't occur, and you can simply show this with an arrow going to our starting materials with no reversibility. The reason, again, it doesn't occur is this pKa difference is too large. It's useful to go through this exercise because you might find yourself with two molecules that you aren't sure how they can react. Now, so far, we've just talked about pKa's of specific protons, but pKa can also be asked about a molecule in general. What's the pKa of that molecule? Well, when that's asked, it's always talking about the most acidic proton on the molecule. And that's because the most acidic proton is the one that's going to do chemistry or acid-base chemistry first. So when we look at the pK of a molecule, we're going to find the most acidic proton. And we can do this because we have a pKa chart. And we can look at different functional groups and decide which one is the most acidic. This pKa of the most acidic proton is going to be used to describe the molecule. And this proton reacts first and is really the one we care about. So I have two examples here, two molecules. Now, when you start to see molecules that are more complex, it's really easy to kind of freak out a bit. No need to do that. We're just going to look and see if any of these protons are somewhat acidic. This is going to become easier with practice. sometimes you have to draw in protons. So here I see a proton on our phenol. It's an alcohol that's on an aromatic ring. And if we look back at the slide before, we see that this proton has a pKa of around 10. Now there's also another slightly acidic proton, and it's not shown, but it's on the end of this alkyne. This proton here has a pKa of around 25. I've highlighted the most acidic protons here, but again, we just care about the most acidic proton, which is the one that will do chemistry. So in this case, the pK of this molecule would be described to have around a pK of 10, okay? And this is our most acidic proton. All right, let's look at the other molecule we have here. So we've got an amine, we've got this nitrogen. We know that these protons here have a pKa of around 35. And then we also have a carbonyl. Very cool. We know that this proton here has a pKa of around 20. Our proton that is alpha, or right beside that carbonyl, is the most acidic. It has the lowest pKa. Remember, lowering our pKa means a stronger acid. So the pKa of this molecule would be described as around 20. This will be really useful when we start to look at if acid-base reactions can happen with certain molecules. Let's combine these two principles together and let's do a practice problem. All right, so let's look at these two molecules and we're going to decide which side of our equilibrium this reaction lies on. So the first thing we need to do is spot the most acidic proton. So I've got a carboxylic acid. This proton here has a pKa of around 5. We also have this proton on the alkyne, which we know has a pKa of around 25. These are our two most acidic protons. What about this nitrogen? Could this act as an acid? Well, the pKa of that proton there is around 35. It's not likely to act as an acid. We have a pretty acidic proton on our carboxylic acid. So this proton here with a pK of 5 will be our acid. So this is our acid. Let's write the pKa of this molecule, which is around 5. Let's draw our arrow pushing mechanism to show this. We have a nitrogen with a lone pair. This nitrogen will pick up this proton, and the electrons between the hydrogen-oxygen bond will move to our oxygen. I like to draw what didn't change first. Okay, it's our alkyne. Then we have our carbonyl. Okay, oxygen. We don't have the hydrogen there. It started out with 2 lone pairs, and then it gained another lone pair, which I'll draw in green. This is the one from our arrow pushing. It now has a formal charge of negative. Let's draw what happened to our amine. This is what didn't change. It had a proton there as well. The lone pair is now gone. Notice this first arrow. The lone pair is gone, and it is now bound to a hydrogen. It has a formal charge of a positive. I'm going to draw this hydrogen here in red, which we decided was the most acidic proton. Cool. All right. We can double check our mechanism to see if the charges make sense. It's neutral on the left. It's also neutral on the right. Great. Now let's look at the pKa's of the left side and the right side. We decided the pKa of this molecule on the left has a pK of 5. It's the most acidic proton on the molecule. And on the right side, we see that we have the proton here on an ammonium cation here. The pKa of this proton is around 10. Now we can analyze this reaction because we know the pKa's of the most acidic proton on either side. We know that the side with the weakest acid is favored. Remember, weak acids have higher pKa's. Remember that strong acids have lower pKa's. I know I've written this many times in this lecture, but it's super important to remember this. So we want the side with the highest pKa. And this is the right side. That means that we know that this reaction can go forward. Now my question is, can it go backwards as well? Well, when we go back and look at our rules here, this pKa difference is less than 6. This reaction is absolutely reversible. It is going to be favored on the right side here because it has a higher pKa and it's a weaker acid. Is favored. So that's it for this video about acid-base chemistry. Here we used our knowledge about curved arrow notation, where arrows are used to show electron transfer. We also talked about pKa's and how we can use them to analyze whether a reaction is favored or not favored. We also now know that the weaker acid is always favored. And that's it for this video, and I will see you in the next video.